the research came from the center that led to this device. So how does it work? Each of my legs has 3 microprocessors and about 12 sensors. So 6 computers and 24 sensors. Get it? And what we've done, again, is we've mapped how muscles and tendons work and how muscles are reflexively controlled by the human spinal cord. And we embed that scientific knowledge in the programming of the microprocessors. So it turns out your calf muscle is controlled with a positive force feedback when your foot's in contact with the ground as you walk. It works very simply. The greater the force borne by your calf muscle, the greater is the activation of that muscle. For those in the audience that understand control theory, this sounds very, very unstable, but it's only active when the foot's in contact with the ground. So when I walk slowly, there's not much energy. I can move quickly, and then I get lots of energy. That's just an emergent response of a positive torque feedback, comparable to what's happening in your body when you walk, assuming you have biological legs. So here's a diagram circuit. This shows just a muscle by a physical model of a muscle tendon. So what happens is the robot measures joint state, position, and speed. That's fed into a muscle geometry chip that converts it to an estimate of the length and speed of the muscle fascicles, virtual muscle fascicles. And then the loop up top is a model of how a particular muscle is controlled by the spinal cord. That's the spinal reflex. So why pay attention to how the human body works? The answer is, what emerges is this tremendous diversity and flexibility. So we designed this device to work for walking, not for running. But this person was fitted with the device and was inspired and decided to run. And we're like, wow, that's interesting, it works for running too. So not surprisingly, when you understand the fundamentals of one motor task, often those fundamentals are also relevant for other motor tasks. So you get this broad diversity of dynamics. So in the previous section, I talked about how to measure signal and get signal into nerves. In this intrinsic control framework, what would one do with a nerve signal? So what we've looked at is using a peripheral neural signal to modulate the sensitivity of that spinal reflexive action. So if I don't have any descending command, if I don't fire my residual muscles, then there's very little sensitivity in that force feedback. But if I really fire my muscles, I get lots of power. So that framework to blend extrinsic and intrinsic control is extremely powerful, because the microprocessors run a very, very rapid loop, and then the slower loop of the human nervous system modulates those sensitivities. So the commercial embodiment of this technology is called the Bionic. Under computer control, it modulates stiffness at foot strike to attenuate shock, and then to promote tibia progression. And then mid-stance to toe off, it applies these torque feedback, high torques and powers. This has been fitted on approximately 1,000 people, half of which have been wounded veterans here in the US. So what is the clinical relevance of this particular example of Bionics? One thing we have shown is that this device enables a normalization of preferred walking speed. So if you ask someone to walk, they have a range of velocity that they operate where they're very, very economically in terms of metabolism. So we've shown with this Bionic device, for persons that are amputated below the knee, that their preferred speed is in fact normal. This is very important for patients. So on the left is the lady wearing the Bionic intervention. On the right is a conventional prosthesis. The conventional prosthesis is typically made of carbon springs without any computation or actuation. So you see the precipitous increase in her walking speed. On the left, she's a community ambulator. On the right, it's very difficult and strenuous to get around. Another thing we've shown, a key metric of gait, is how much food energy a person uses to transport unit weight, unit distance of their body. That's plotted here in the vertical axis. On the x-axis is how fast a person walks. The red data are a person wearing dumb, passive devices without any computation or actuation. The blue data are from the same person wearing a bionic limb. And the green data are age, weight, height match persons with normal biological limbs. There's no statistical difference between the person wearing the bionic limb and the person using completely normal physiological limbs. So if you put a black box around a human, you cannot tell by measuring the amount of energy they use and the speed with which they walk, whether they have natural limbs or bionic limbs. Wow, we're making progress. This is what it means for this